Okay, so yesterday what we were looking at is we looked at inductive reasoning. Inductive reasoning and conjectures. Inductive reasoning is basically finding a pattern, looking at something and detecting whether or not there's a pattern in the relationship of the numbers or in the relationship of the drawings. And then we drew a conclusion from that inductive reasoning that we called a conjecture. Conjectures can be true and they can be false, because a conjecture is based on that inductive reasoning, which is probably based on a finite number of examples. We can't possibly run every single pattern sequence that we see, so we make a conjecture based on the ones that we've experimented with. So if we look at the next part, this is a counterexample. A counterexample is an example that proves the conjecture is false. So I make a conjecture, and then you make a counterexample to prove that my conjecture was false. So Kate and Carrie are given the following number pattern by their teacher. 2 squared plus 1 is 5, which is a prime number. 4 squared plus 1 is 17, which is another prime number. 6 squared plus 1 is 37, another prime number. 10 squared plus 1, 101. 20 squared plus 1, 36 plus 1. So Kate's task was to make a conclusion based only on the number patterns shown. So Katie's conclusion would be when I square an even number, because all of these numbers were even, and then add 1, the resulting number was a prime number. Katie's conclusion is considered to be a conjecture based on what? Inductive reasoning. So that was Katie's task. Perry's task was to see whether or not there was a counterexample for this. Can you determine a counterexample? Can you think of an even number that when I square it and add 1, I do not get a prime number? That's not an even number though. It has to be an even number. So look at the list that I have there. What even numbers do I already have? I have 2, 4, 6, I have 10, I have 20.
8.
What's 8 squared?
64.
What's 64 plus 1?
65.
Is 65 a prime number? What's a prime number? No, that's an odd number. A non-even number would be odd.
Isn't it like the way it can be divided by itself and 1?
Yeah, a prime number has 2 factors, itself and 1. Does 65 have just 2 factors? I can divide 65 by 5. So if I can divide it by anything other than itself and 1, it's no longer a prime number. So 65 is not a prime number. So this counterexample negates Katie's conclusion. And there are more examples that I could use. I could use 12 squared plus 1. 144 plus 1. I get 145, which, because it ends in a 5, means I can divide it by 5. So again, it is not a prime number. So sometimes when I have a conjecture that's shown to be false, what I could do is I could revise the conjecture. So let's look at class example number 3. Mick and Sue are discussing the conjecture that could be made regarding the prime number pattern shown. These are all prime numbers. 3 plus 5 is 8, 5 plus 7 is 12, 7 plus 11 is 18, 13 plus 17 is 30, 19 plus 23 is 42, and 29 plus 31 is 60. So they both agree to the following conjecture. The sum of 2 prime numbers is an even number. Can you give me a counter example? What's the first prime number? Or what's the smallest prime number? 2. What are all the rest of the prime numbers? What kind of numbers are 3, 5, 7, 11? They're all odd numbers. If I take 2 and I add it to any odd number, what would I get? What did I get? 2 plus 3 is?
5.
What kind of number is 5? It's an odd number. If I took 2 and I added it to 13, I'd get another odd number. So, is 2 the only even prime number I have? Yeah. Because every other even number can be divided by 2. So 2 is the only even prime number. So 2 is the only number that when I add it to the rest of these prime numbers is going to give me an odd number. Because I'm already at an odd, add one, add another one, I'm going to be at an odd number again. So what I could do is I could revise this conjecture. Instead of saying the sum of 2 prime numbers is an even number, I could put in the sum of 2 prime numbers, not including 2, is an even number. And then C says, make a conjecture based on the number pattern if the condition prime number was removed. So if I remove the condition of a prime number, what were the rest of these numbers? What types of numbers were all of these ones? Odd. So the sum of 2 odd numbers is what? What were these numbers? Even. So all we're doing at this point is making conjectures, disproving them with counterexamples, or stating the conjecture through inductive reasoning, so through a set of patterns or a set of examples. So Jerome investigated the following number patterns. 1 plus 2 plus 3 is 6. 5 plus 6 plus 7 is 18. Negative 6 plus negative 5 plus negative 4 is negative 15. And negative 12 plus negative 11 plus negative 10 is negative 33. So what he noticed is these are 3 consecutive integers. Consecutive means they go in a row. 4, 5, 6, 10, 11, 12. 21, 22, 23. Those are consecutive numbers. So it says write 2 more patterns using the sum of 3 consecutive integers. So give me a number.
Make any number.
Yep. 5. Well, we already kind of have 5 as a starting point. Give me a different number. 10. 10 plus 11 plus 12 are consecutive numbers. If I add them together, what do I get?
33.
Okay. Give me a negative number.
Negative 3.
So negative 3 plus negative 4 plus negative 5 equals?
Negative 12, 13.
Which one is it?
4.
6 statements, do you notice something about these 3 numbers, or maybe about one of those 3 numbers and this answer? So use inductive reasoning to make a conjecture based on the sum of these 3 consecutive integers. I could say that the sum, the sum of 3 consecutive integers is equal to what? The middle number times 3. This is a conjecture. Okay? It is not a full-blown conclusion. We've proven it for these 6, plus the couple of others that I had done and I had erased. It is not a proven fact for every single one. In order to draw that conclusion, I would have to use logical or deductive reasoning, which is what we're going to do next week. Talia.
Would that work if you had 5 consecutive?
So if you graph this, graph that for me right now. Grab your graphing calculators.
This is how you graph, right? It's like
When Dawn graphs this, this is what she sees. That's what she sees on her screen. So that leads her to the conjecture that the domain for this equation has to be all the x values that are greater than 0. So my counterexample would give me an x value that's less than 0. So give me a number that's smaller than 0, guys. Quickly.
-2.
Okay? So if I put -2 into this equation, I get y equals -2 to the power of -2. And what is -2 to the power of -2?
-0.2.
Be positive 0.25.
Oh, right.
So I get positive 0.25 or 1/4, which means this is valid. So the domain from Dawn is not true. Okay, so your questions that I want you to work on. I gave you question number 1 yesterday, so it'd be question 4, 5, 7, and 10.